morning. Let me start off by recapitulating what had been done in the last class. We had started discussing the dynamics of the expanding universe, and we were using Newtonian mechanics and Newton's law of gravity to discuss the dynamics of the expanding universe. If you remember, in the first lecture I had told you that we will assume that the laws of physics which we believe are valid in our neighborhood on the earth, in our solar system, can also be applied to distant parts of the universe. So, so we had considered an observer O, and we were looking at the equation of motion of a test particle, a galaxy. We considered an observer O, and we were looking at the equation of motion of a test particle, a galaxy, a distance r away. And for this galaxy we wrote down the Newtonian equation of motion. The mass of this test particle cancels out from both the left, it appears on both the left and right hand side. So, it cancels out from this whole equation. And then we had, so the acceleration of this test particle is determined by just the mass inside this sphere of radius r, and we had this equation of motion. The acceleration is minus g m by r square essentially, and we had written that in the vectorial form. Now, next we had gone over to the co-moving coordinate system, a coordinate system that expands, that is fixed with the galaxies which are moving apart from one another. So, as the universe expands, the position of the galaxies remain fixed, but there is a scale factor A which increases with time, and the scale factor A, then it turns out from this that the scale factor A satisfies this equation. We were interested in solving this equation. Now, in this equation, remember, rho, the density, was not a constant. As the universe expands, the density falls because the mass is conserved. So, rho into a cube is a constant, the volume goes as a cube. So, rho into a cube is a constant, and we had written this constant as rho naught, the present density, into a naught cube, where a naught is the present value of the scale factor, which we assumed had a value 1. So, we had this differential equation for the scale factor, and we had this relation for the density. So, using these two, we could eliminate the density from this differential equation, and what we did was we multiplied it with a dot on both sides, and doing that we could convert this equation to this form: half the time derivative of a dot square is equal to 4/3 pi g rho naught into the time derivative of 1 by a, and this could be integrated. Once you integrate this equation, you get, we had a constant of motion E, the first constant of motion E. Now, the behavior of this equation, I had told you, is exactly the same as that of a ball thrown from the surface of the earth. The radius, the distance of a ball thrown from the surface of the earth, or thrown from outside the earth essentially. And there are, so this was the equation. E corresponds, I had told you in the last class, to the energy of that ball, and there were three possibilities. There were three possibilities. Let me show you these three possibilities. These three possibilities correspond to different values of E. If E was negative, the ball thrown from the surface of the earth falls back, does not have the escape velocity. Similarly, the universe that is expanding, the scale factor, we are somewhere here now, the scale factor is increasing with time. In the future, if E is negative, then the universe is going to collapse again. If E is 0, it is like a ball with just the escape velocity. So, it will go all the way to infinity, the expansion, but it will come to rest at infinity. And if E is positive, it will have a finite velocity at infinity. These were the three possibilities. And which possibility we have depends on the value of E. So, next we had discussed how you can observationally determine the value of E, in principle at least, a possibility. This possibility though is not possible, it is not feasible to realize this possibility. So, what you could do is you could divide this whole thing by a square multiply by 2. So, you get an equation which has the Hubble parameter square over here, the density over here, and the value E, the constant E over here. Now, we could take 3 h square by 8 pi g, we could take this factor 8 pi g and 3 common outside. Once you do this 3 h square by 8 pi g, 3 h square by 8 pi g is something that we define as rho critical, and if you divide throughout by rho critical, then this equation for E becomes this, right. So, the definition of rho critical, the critical density the critical density, let me put it somewhere else, the critical density rho c is 3 h square by 8 pi g, and the ratio of the actual density to the critical density is what we call the density parameter omega. If omega is more than 1, it means that the density is more than the critical density. This term is larger than this term, so E is negative. If the density is less than the critical density, omega is less than 1, E is positive. If the density is exactly equal to the critical density, then these two terms exactly cancel out, E is 0. So, the value of E is determined by the Hubble parameter and the actual density of the universe, and it is convenient to quantify the Hubble, convert the Hubble parameter to an equivalent density. How? Take the Hubble parameter, square it, 3 multiplied by 3 divided by 8 pi g, that gives us a density called the critical density, and the ratio of the actual density to the critical density decides the value of E. And I had also worked out the value of the critical density. Now, after having done this, omega naught is the present value of the cosmological parameter, the present value of the ratio of the density to the critical density. So, having done this, we had explicitly worked out one solution. We had worked out the solution where omega is 1, the constant E is 0. This solution is easy to work out, and what we had obtained was that the scale factor goes as t to the power 2/3. This is very important. This is the critical cosmological model. So, this cosmological model goes as t to the power 2/3, the one in black, the one which has omega E equal to 0 or omega equal to 1. Now, we worked out this in the last class, and then we also calculated how does the Hubble parameter depend on time, and it turned out that the Hubble parameter was 2/3 1 by time, which also told us that at any instant of time the age of the universe was 2/3 1 by the Hubble parameter, or 2/3 the Hubble time. Now, remember that in the freely expanding cosmological model, the age was 1 by h naught. So, the age is smaller if we take into account the effect of gravity. That is one point which you should remember, and we can explicitly work out the age in different cosmological models. We shall derive a general formula for this maybe today or in the next lecture. Now, I leave it for you to work out the solutions for different values of E. So, it is an exercise which you should do to work out the solutions for different values of E or different values of omega. We have worked out the solution for E equal to 0 or omega equal to 1. It is as an exercise for you to work out the solution for different values of E. Now, Let me switch over, let me move forward to a slightly different issue. The issue is one of pressure. Let me start off by briefly recapitulating what we mean by pressure and calculating it using a very simple form of kinetic theory for a particular case. Let us consider a box I have only drawn a section 2 dimension. Let us consider a box with particles. So, there are particles inside this box. And it is filled with particles. Now, we will assume that these particles are relativistic particles. They are not the typical atoms and molecules that you see. I am sure you must have done kinetic theory for the atoms and molecules that you see. Let us just jump and do the same thing, assuming that we have relativistic particles moving randomly. So, it is a relativistic gas, a gas of relativistic particles. What do we mean by a gas of relativistic particles? You could think of this as a gas of photons. There is a cavity filled with photons moving randomly inside this cavity. So, the photons inside have random motions, just like the gas inside a cavity. We know that a gas inside a cavity, the molecules have random motions, they move in all directions with equal probability. So, similarly, let us consider a cavity which has, let us say, photons. This is valid for any kind of relativistic particle. By relativistic particle, we mean particles that move at the speed of light. Okay. Particles which move at the speed of light. So, if neutrinos are massless, they could be neutrinos, or any even if you have electrons or atoms moving at very high speeds comparable to the speed of light, then the fact that they have mass becomes irrelevant and you can treat them as relativistic particles. Okay. So, let us consider a gas, a box full of relativistic particles. So, for these particles, let us assume that they all have the same energy E. The argument that I am going to place does not depend on this assumption. So, I am going to make the simplifying assumption that they all have the same energy E. It goes through even if you assume a distribution of energies. So, the particles all have the same energy E, and we know that for a relativistic particle, the fact that the particles are relativistic comes in over here. We know that for relativistic particle, the momentum, how much is the momentum of a relativistic particle? Does anyone know? It is, so the momentum is E by C, right. So, for a relativistic particle, the momentum is E by C. So, it has energy E and momentum P, which is E by C. Now, let us consider a particle that comes and hits this wall and then bounces off it. Okay. Let us say that this angle is theta. So, the change in the momentum, the delta p that occurs in the x direction, we are dealing with the change in the momentum only in the x, there will be a change in the momentum only in the x direction, the y direction of the momentum is conserved and there is no, the z direction is also conserved. So, we are calling this the x direction, this is the y direction, we are interested only in the x direction, x along the x axis here. In this problem it is only the x axis that is of consequence. So, the change in the momentum along the x direction, that is the only change that occurs how much is that? 2, yeah, it is 2 p cos theta, the x component gets reversed. So, there is a change of 2 times the x component, which is p cos theta, or we can write it as 2 e by c cos theta. Now, we would like to calculate the rate of change of momentum per unit area per unit time, that is what is pressure. Rate of change of momentum, sorry, just the rate of change of momentum per unit area. Time, when I say rate, time is already there, right. Rate of change of momentum is force, per unit area makes it pressure, right. So, force per unit area is pressure, that is what we are interested in, and pressure acts normal to the surface. So, we are interested in the x component of the force only, right. Now, if the number, now, so we have already calculated the change in the momentum when one particle collides. Question is, per unit area in 1 second how many particles are going to collide, what is the rate at which the particles are crossing this surface. The rate at which the particles are crossing this surface is how much? It is the number density of particles into the speed with which they are moving, right. So, the pressure straight away we can say is 2 E by C, this is the pressure, remember, into the rate at which they are crossing this. So, that is the number density of particles. There is a factor of cos theta E by C cos theta here. So, this number density of particles in the rate is C cos, there will be a factor of cos square theta now. Why cos square theta? 1 cos theta from here and 1 cos theta, because the rate at which they are crossing this is the x component of the speed into number density. So, the pressure is 2 E by C into the number density into C, that is into cos theta, cos square theta, and what I have to do is I have to take the average value of cos square theta, because the particles are moving randomly, there will be particles coming in all directions. So, I have to calculate the average value of cos square theta. How do we calculate the average value of cos square theta? So, we want to calculate the average value of cos square theta. So, this is going to be, we have to integrate cos square theta over all possible angles, all possible directions of motion. So, we have to integrate over all solid angles, and in spherical polar coordinate system we know that this becomes the integral 0 to pi d theta sin theta d theta into d phi, where the integral over phi is 0 to 2 pi, and we are interested in the average. So, we have to divide by the total solid angle, which is 1 by 4 pi, and we have to divide by a factor of 2, because only all solid angle means that there will be particles going exactly in the opposite direction also, which will never cross this. Cos square theta does not distinguish between this direction and this direction. So, we have to divide by another factor of 2, because the particles moving in the opposite direction, we are interested only in the particles moving this way, we are not interested in the particles moving like this, we are not interested in these. So, we have to divide again by a factor of half. Okay. So, the phi integral is very easy to do. So, I have 1 by 8 pi, the phi integral gives me 2 pi straight away, and if I substitute mu equal to cos theta, then this integral becomes minus 1 to 1 mu square d mu. Okay. And if I do this integral, what I get finally is 1 by 8 pi and 2 pi. So, basically I did 1 by 4 pi, 1 by 4, and this gives me 2 by 3. If I integrate this, I will get 1/3 and the limits will give me 2. So, this will give me 2 by 3. Finally, I have 1 by 6. So, the average value of cos square theta is 1 by 6. So, substituting that in my expression, what I get is that the pressure is 1/3 the energy of each particle into the number density of particles, which is essentially 1/3 into the energy density epsilon. Number density into the energy per particle is the energy density. So, the pressure for a relativistic fluid is just 1/3 the energy density. Okay. Now, you may be wondering, why am I discussing pressure? What relevance does it have to cosmology, to our discussion as a whole? So, let me now explain this. So, what is the relevance of pressure? Let me just explain this first. Now, we have been doing a Newtonian analysis. The Newtonian analysis, in the Newtonian analysis, the gravitational force from inside on this object occurs only due to the mass distribution inside this. Now, in this does not hold in general relativity, this is not precise in general relativity. In general relativity, there is a modification. The modification is that the energy density inside this contributes to the gravitational attraction. Not only that, if there is considerable amount of pressure, then the pressure also contributes to the gravitational attraction. Now, for the kind of matter that we were discussing to start with, the energy density was just rho c square. The matter was at rest or moving moving at relativistic speeds, not having relativistic random motions. So, for such a situation, we could it reduces to the Newtonian result, since the pressure is negligible and the energy density is rho c square. But suppose our universe is filled with a fluid that has significant amounts of pressure, then the Newton's law is no longer valid. You have to put corrections over here, and these corrections come from Einstein's theory. Okay. So, we have to take into account the possibility that the material that fills the universe may have pressure, and once you wish to incorporate that, then you have to modify this. Not only do we have to modify this, we also have to modify this, the conservation of mass. So, let me first discuss what happens to the conservation. Before that, let me explain to you that for galaxies the pressure is negligible. To explain that, and the analysis that we have been doing till now is correct. To explain that, let us just go back to the definition of what we mean by pressure. Pressure arises because of random motions. Now, these galaxies, it has been observationally found, are on the average moving away from us with the speed proportional to the distance. Question is this random motion? Suppose the whole gas itself were moving, would that be pressure? No, right. So, the motion of the galaxies away from us is not pressure. What would be pressure? What would give rise to pressure? What gives rise to pressure over here? The random motions. So, the random motions of the galaxies, if these random motions are important, then we shall have pressure. If the random motions are not important, not very large, then the pressure is negligible. It turns out that the random motions, so for galaxies, the random motion, random component of the velocity. So, the deviations from Hubble flow, random velocities, these are of the order of few hundred kilometers per second, hundreds of kilometers. Okay. So, I am writing 100, it may be few hundred, but now the question is, then is this pressure, is the pressure produced by this important or not? The pressure becomes important if P, the pressure, by c square is comparable to the mass density rho, or P is comparable to rho c square. Okay. And the pressure we know is of the order of the rho into the v square, it is of the order of rho into the random velocity squared, right. So, if I divide this, so the condition essentially boils down to that the random motion v by c should be of order unity if pressure has to be important, which is why we are interested in the relativistic gas. The relativistic gas, the particles have random motion which is exactly equal to c. Now, how much is this ratio for 100 kilometers per second? How much is the speed of light in kilometers per second? Three into 10 to the power 5. So, for these galaxies we have 10 to the power 2 divided by 3 into 10 to the power 5, which is of the order of 10 to the power minus 3, which is much smaller than 1. So, the effect of pressure is negligible for the random motions of the galaxies. Now, what are the modifications that occur when we have pressure? The first modification that we shall consider is as follows. When there is, so consider a part of the universe, okay. Let us say that this has comoving volume 1, it has comoving volume 1. So, its volume at any given instant is a cube, right. It has comoving volume 1. So, its physical volume at any instant is r cube, which is a cube. Is it okay? Right. So, there is a part of the universe which has this volume. Now, the expansion of the universe we assume is adiabatic. We assume that the expansion of the universe is adiabatic. What do we mean by this? What we mean is, as the universe expands, we are looking at a part of the universe, there is no heat exchange between this part of the universe and the next. One justification could be that the universe is homogeneous and isotropic. If it is homogeneous and isotropic, the temperature here will be the same as the temperature in the other part of the universe. So, there is no reason why heat should flow, right. Or you could just take it as an assumption that the expansion is adiabatic. Now, if I have, we know from first law of thermodynamics that for this volume du plus P dV is equal to the heat that flows in or out, and if it is adiabatic expansion, then this has to be 0. Now, the internal energy du is the energy density into a cube, right. Internal energy is the energy density into a cube. So, plus the pressure. Now, we will assume that the pressure P is equal to some constant W into the energy density E. Okay. We will assume that the pressure is some constant into the energy density E. This is called the equation of state. So, we will assume an equation of state that looks like this. P is a constant into the energy density. Now, you may ask, what is the justification for such an assumption? Maybe it is something else, the pressure, right. But we have already seen that for galaxies pressure is 0. So, that is called dust. Dust refers to a medium which has 0 pressure. Okay, the particles have very little random motion. So, for dust we see that pressure is 0. So, what is the value of this W? 0. For relativistic fluid, a relativistic gas, what is the value of W? 1 by 3, right. So, we have two examples at least where this kind of an equation of state holds. So, we will assume that whatever fluid it is that fills the universe, maybe there are maybe 2, 3 things, components that fill the universe. The equation of state for all of them can be written like this. Okay, let us assume this. So, the pressure can be written as like this and the volume is d A cube. So, this should be equal to 0. So, we can expand this out, and if you expand it out, what you get is A cube d epsilon plus epsilon d A cube plus W epsilon d A cube is equal to 0. So, we could divide throughout by A cube and epsilon. Dividing throughout by A cube and epsilon, what we have is d epsilon by epsilon plus, now there will be two terms. So, we have 1 plus W into d A cube by A cube is equal to 0. So, this is d of ln epsilon plus d of ln A to the power 3 into 1 plus W ln A cube into 1 plus this is the same as this. So, we have the fact that this is equal to 0, or it essentially tells us that epsilon into A to the power of 3 into 1 plus W, this should be equal to a constant. So, this should be equal to epsilon naught, the present value of the energy density. A naught we have assumed to be 1. Now, the energy density, it is convenient to write it as rho c square. So, remember this rho is the energy density in units of c square. If it is the usual ordinary matter at rest, then the energy density is essentially the mass density into c square. Okay. So, this also tells us equivalently that rho A to the power 3 1 plus W is equal to rho naught. So, let us check first whether this matches with what we have already learnt. Pressureless fluid, a pressureless fluid is what we refer to as dust. Let us take up two cases. So, for dust we have pressure equal to 0 or W equal to 0. So, let us put W equal to 0 over here, and we recovered the familiar conservation of mass, rho into A cube is a constant. So, we have rho A cube is equal to rho naught. Let us next take up a relativistic gas. For a relativistic gas, we have pressure is equal to 1/3 rho c square, or W is equal to 1/3, which tells us that rho 1 plus W is 4/3. So, it tells us that rho into A to the power 4 is a constant if W is 1/3. So, in this case we have rho A to the power 4 is equal to rho naught. So, we see that the way the density changes as the universe expands depends on the pressure of the medium. This is something which has to be incorporated when we allow for the possibility that the content of the universe, the constituent of the universe, has pressure. Okay. Now, so as the universe expands, the density does not fall as 1 by A cube, it falls as 1 by A to the power 4. Which is it faster or slower than this? The density here falls as A to the power minus 3. Here the density falls as A to the power minus 4. Which one falls faster? The radiation, for radiation, with the expansion of the universe, the density falls faster. The universe becomes double. What happens to the density? What factor does it fall? 1 by 8. The universe becomes double in size. What happens to the density? 1 by 16. It falls faster. Can you explain to me why? How? What happens why is the conservation of matter as we know it, what we call conservation of matter, why is it violated? How come the density falls faster? Isn't matter conserved? So, the point that should be borne in mind in this kind of an approach, what is happening is that it is the conservation of energy which is taking place, energy is conserved. Now, as the universe expands, the gas inside this does work. There is a gas, if the container expands, the gas inside does work on the walls of the container. The pressure does work. The pressure is acting outward, so the pressure if this expands, the pressure does work on the walls of the container. Okay, so the pressure actually does work as this expands, and some of the energy goes into that. As a consequence, the energy density falls faster than it would if there was no pressure. Okay. So, this is one way in which you can understand. There are various other ways also in which one could understand this, but this is one way in which one could understand why the energy density falls, the mass density falls faster for a relativistic gas where there is pressure. So, the way in which the density varies depends on the value of the pressure. That is a point that has to be borne in mind. And for an equation of state of this type, we have just derived how the density varies with pressure. We have just derived the relation which is given over here. So, rho into A to the power 3 into 1 plus W is a constant. Okay. Now, so this is one modification that occurs because of pressure. Now, let me discuss another modification that occurs because of pressure. We have to incorporate both of these modifications. In Newtonian gravity, the acceleration of this test particle of this galaxy is due to the mass inside this sphere. Now, if you take Einstein's equations, Einstein's theory of relativity and work out the same thing, it turns out that the acceleration of this test particle is not exactly this. The correct thing, the correct thing expression is let us just remember this, rho, the acceleration is minus 4/3 pi g rho into r. This comes from just the Newton's 1 by r square law. Okay. Now, there is a modification, and the modification, let me write down the correct one. So, in Einstein's theory, and those of you who have some idea of general relativity can check this up. In Einstein's theory, this gets modified, and what we have now is that the acceleration is equal to minus 4/3 pi g. Instead of the density, we now have rho plus 3 p by c square into r. So, this is the modification that has to be incorporated. So, this, remember, comes from just the Newton's laws, that the acceleration is g into the mass of the test, the acceleration is g into the mass contained within the sphere divided by r square, and the mass was 4/3 pi rho r cube. Now, this gets modified in Einstein's theory. It is not just the matter, the mass or the mass density, it is the energy density and the pressure both that contribute. That is the main point to remember. So, finally, if you work out the finally the acceleration is minus 4/3 pi g rho plus 3 p by c square into r. If there is no pressure, or the Newtonian prediction does not have this term due to pressure. This is the extra contribution that comes from Einstein's theory of relativity. So, this is the acceleration on a test particle on the surface of a sphere. Okay. So, we can now convert this equivalently to an equation for the scale factor. So, the scale factor satisfies the equation A double dot is equal to minus 4/3 pi g rho plus 3 p by c square into A or if you make an assumption that you have an equation of state where the pressure is W times the energy density, the mass density. So, if you make an assumption that the pressure P is W times the energy density, and the energy density can be written as rho c square. So, essentially the pressure P is W rho c square. With this assumption, what you get is A double dot is equal to minus 4/3 pi g, and we can take rho common outside, or we can take rho into A, and then we have 1 plus 3 W. We have just put in the equation of state that the pressure is W into rho c square, nothing more, which we had assumed earlier. So, we get this equation for the scale factor. It is just a simple modification of the Newton's laws. So, this is the equation which we now have to solve. We have already solved, we have already discussed the situation where there is no pressure. Now, we would like to discuss the situation where there is pressure. We will generalize it even further. We are going to consider a situation where the universe is not one fluid, it is not filled with one material. In the previous discussion, remember, we had assumed that the universe is filled with only galaxies which have no pressure. Now, I have already told you that there is the cosmic microwave background radiation. I have not told you much, but I have told you that there is a radiation at whose temperature now is 2.73673 Kelvin that fills the whole universe. So, this is a relativistic gas that fills the universe, right. So, the universe could have 2, 3, 4 kinds of constituents filling it. There could be 2, 3, 4 kinds of things in the universe, right. There could be one kind of material which has no pressure, another part which has 1/3 rho c square. The densities could be different in each of them. Now, we know that from the equivalence principle that they all contribute in the same way to the gravitational force. So, they will all contribute in exactly the same way to the gravitational acceleration. Gravity does not distinguish between these. So, generalizing this one more step, what we have is this, that A double dot is equal to minus 4/3 pi g minus 4/3 pi g. The scale factor is the same for all of the medium A, and then we have a sum over I 1 plus 3 W I into rho I, right. So, we can have I could take values 1, 2, 3, 4, 5 corresponding to different constituents of the universe, and each constituent rho I, the energy, they do not exchange energy with each other, they only interact. So, we are assuming that we have these different constituents, they interact with each other only through gravity. That is the assumption we are doing, it is a simplifying assumption. So, the energy density then of each of them is individually conserved, the energy of each of them is individually conserved. So, rho I into A to 3 to the power 3 1 plus W I, this is equal to rho I 0, right, the current value into A to the power this thing, but A naught is 1. So, this refers to the present value of that particular component. So, we could have different components I equal to 1, 2, 3 depending on the cosmological model you want to make up, build up. And we would like to now solve this. It is just a generalization of the situation that we have already dealt with. We have already dealt with the situation where there is only one kind of constituent that has no pressure. Okay. So, we want to integrate this equation and we will proceed in exactly the same way as we have done for the situation where there is only one constituent. So, how did we proceed? Recollect. We multiplied, first thing that we did was to multiply this equation with A dot. So, we will multiply this equation with A dot. Let me go through it slowly, step by step. Okay. Before that, we first have to replace this function of time with this constant, and we have to write this with only one unknown function of time, right. So, because here we have two unknown functions of time, one of them is the scale factor, other is the density. Not one, there are not two, but many. Each density is an unknown function of time. So, I can have three kinds of constituents to three unknown functions of time in addition to the scale factor. So, let us eliminate these unknown functions of time. So, what we have is A double dot is equal to minus 4/3 pi g A, then we have the sum over I 1 plus 3 W I, and then we will replace this, we will replace rho I using this. So, we have rho I naught A to the power minus 3 into 1 plus W I. Okay, so now we have an equation which has only one function, unknown function of time. How do we proceed? Recollect how we had proceeded, and we multiply with A dot. So, let us also multiply this with A dot. So, the left hand side of this equation is straightforward, or it is half now. The right hand side is a little more complicated, not very complicated. So, let me take this up afresh in the next class. Let me stop here for today and let me take this up when we start afresh in the next class.